All right. We are recording right now. First, Chapter 6 deals with chemical equations. In the last chapter, in Chapter 5, we started dealing with chemical bond, which is a chemical reaction. The formation of a bond is a chemical reaction. So this chapter, what we're going to do is representing that chemical reaction, making sure that we're writing it, representing it in a way, shortening it in a way, so we can describe what actually happened within our chemical reaction. So first, chemical formulas use this shorthand way of describing the atoms that make up a molecule or a compound. Could be also a formula unit, as we learned in the last chapter. Okay? Chemical formulas will tell us two things, right? What are the two things that a chemical formula should tell us if it's describing the atoms that make up a combination? What the elements are and how many of them there are. Okay? So, chemical formulas show us two things. Shows us the type of atoms that are in the compound, represented by the element symbol, and the number of each type of atom that's in the compound, generally represented by a subscript. Not generally, represented by a subscript. Chemical formula shows two things. The kind of atom, and then the number of each kind of atom that are in that compound. Good there? So, if we take a look at some formulas, right, we won't do all 6 of them, but there's 6 of them that are written right underneath there, okay? Here, what would we say about this chemical formula? What is this telling us here? There's what? There's one, sorry, take it. Good. 4 chlorines, 1 carbon. Okay? Then here, right? If we don't have any subscripts, what do we say that makes? Just 1, right? So 1 sodium, 1 bromine. Okay? Here, 2 aluminum, 3 oxygens. Okay? Then start getting a little bit more complex, right? When we had those polyatomic ions, we had to use the parentheses to represent the number of groups, right? So this subscript counts for everything that's inside the parentheses. So for this formula here, how many magnesiums? Just 1. So how many oxygens? 2 oxygens and 2 hydrogens. That's different than, say, if we wrote this, MgOH2, right? If we wrote that, right, that 2 now only would count for what? It would only count for the hydrogens. Okay? Good there? Right. So then, here, how many calciums? 1 calcium. How many nitrogens? 2. How many oxygens? 6 oxygens there. Okay?
3 multiplied by 2.
Each group here each group consists of 1 nitrogen and 3 oxygens, right? But then we have 2 of those groups. Okay? And then, holy cow, right? How many calciums? 3 calciums. Calcium is not P. Phosphorus. And how many oxygens? 8 oxygens. Okay? Good there? Questions on that? 8. All right. Next, chemical equations. Chemical equations are used to show what is present before and after a chemical reaction. And we said a chemical reaction, I hope we got here, a chemical reaction is just a fancy way of saying what? What happens in a chemical reaction? 2 things combined and they form a? Yes, by forming a bond, or, right? Okay. So, chemical reactions are just a fancy way of saying bond formation. Okay? And sometimes we'll find out here a little bit later on that it could also be bond destroying. It could be making or breaking bonds. Okay? So, chemical reaction is any process where a chemical change occurs and a new substance is produced. How do we know that a chemical change has occurred? We said there are 4 ways that we can generally tell if a chemical change has occurred. What are our 4 indicators of a chemical reaction? Color change is 1. Formation of gas. Formation of precipitate. And more generally, as far as the temperature change, a release of energy, which could be light, but a lot of times is heat. Okay? So those four things: color change, formation of gas, formation of precipitate, energy given off in the form of reaction. Generally, how do we know that a chemical change has occurred? Are four indicators of chemical change. Okay? All right, good there. There's a little question that you have to answer right there. All right, some more fill-in-the-blank stuff. So, general form of a chemical equation. Reactants on the left, products on the right. Okay? Most of you could probably figure out what a product is, right? Yeah. And what's product going to be? That's what we end up with, right? So, substances that undergo our change are referred to as the reactants. The stuff that is reacting. Formed during the reaction are called products. A little sassy. Here's how I basically had to reteach 2 weeks worth of class in half an hour before the test started. All right, we good there? Yeah. Here's the more important part as far as this is concerned, as far as this chapter is concerned. Okay? First, conservation of mass. Hopefully something that we know about already, right? During a chemical reaction, the mass of the products must always equal the mass of the reactants. Whatever we start with, we have to end up with. If it was there at the beginning, it has to be there at the end. Does it have to be exactly arranged the same way that it was at the beginning and the end? No. No, but it's got to be there, right? What does that mean for us? In this chapter, mass is never created or destroyed, it only changes forms. Okay? For us, that means, okay, conservation of mass, sorry. I should really read my notes so I know what's coming up next. You don't just keep giving me these big intros and then I don't fall apart. As far as that's concerned, though, that leads us to balancing equations. Okay? This is something that we got exposed to a little bit last year. We will do a lot more of it this year. All right, settle in. So, what does this mean? This means that because mass is conserved, okay, the number of each kind of atom has to be the same in the reactants as it is in the products, right? If we start with 6 oxygen atoms in the reactants, what has to be in the product? 6 oxygen atoms, somewhere, somehow, okay? They don't have to be joined to the same thing that they were at the beginning. A lot of times they're not. That's what a reaction is, okay? But they have to be there. When the number of each type of element is exactly the same in the reactants and the products, we say that that equation representing the reaction itself is balanced. Okay? Yay. I know, it's very exciting. Good there? Here's an important rule that we have to make sure that we remember. Okay? 1. Well, really the only important rule. Okay? A chemical equation must be balanced by adding coefficients in front of formulas and not by changing subscripts in the formulas. We'll talk about what that means in just a second. If we change a subscript, what are we doing to our formula? You're adding or taking out an atom, right? And what does that result in? That's something different, right? If we have water, H2O, and we add another oxygen atom and make it H2O2, right? That's something completely different. Okay? So we can't do that when we're balancing equations. We have to add coefficients, and we'll talk about what that means in a second. Are we ready? You actually have this whole progression right there. It's actually sideways in your paper, just like it is all together. But so we start off with this chemical equation. H2 plus O2 gives us H2O. Okay? The arrow represents produces or results with. Okay? So hydrogen gas plus oxygen gas gives us water. Right? And based on our formula, H2 means that there's 2 atoms of hydrogen. O2 means there's 2 atoms of oxygen. And then over here, right, H2O means there's 2 hydrogens and 1 oxygen. Is this equation, as it's written, a balanced chemical equation? No. Are there the same number of each kind of atom left and right? There's not. So here's what we do. Okay? We know that in order to get 1 molecule of water, 1 electronically neutral group of atoms of water, we need 1 oxygen and 2 hydrogens. Okay? So, the 2 hydrogens, sure, the 1 oxygen, right, then goes and forms a compound, right? But what will we then be left over with? 1 what? Oxygen. Is oxygen going to stay by itself?
No.
No, it's not. It's looking to pick up 2 electrons, right? So, what might we do to help out here? Okay. If we have another 2 hydrogens, right, what would those 2 hydrogens then do? Bond with the oxygen, and now we end up with more water, right? So, okay, that second oxygen atom, right, goes and forms a compound with 2 other hydrogen atoms. Okay?
It was a huge spider.
In order for both of these oxygen atoms to form a water molecule, how many hydrogens do we need?
2.
Well, we need how many total? 4, because each oxygen needs 2 hydrogens. Okay? So here, can we do this? Answer is no. Can we do this? No. This is different. You can't change the subscripts. H4 is something different than H2, other than the fact it never exists. But, okay? That would be something different than H2. So what do we do here? Oh, not that. We now add a coefficient in front of that hydrogen. Okay? We need 2 of these H2 groups in order to make water molecules with both of these oxygens. How many water molecules do we end up making? How many water molecules do we end up making? We end up making
2.
What? 2. You end up making 2 water molecules. But in order to do that, you need 2 oxygens and 4 hydrogens. Is this reaction up here, H2 plus O2 equals H2O, any different than this reaction down here? Is this still H2 plus O2 equals H2O?
Yeah.
It is. But all we've done is change the amounts of the H2 and the O2 to make sure that we're balanced on both sides. Does that make sense?